Dear student, hello. We start our new lecture on formal language automata and codes. And today we will have lecture number 19. This lecture is devoted to the following topic: complete sets. And this lecture you can find in my web page here, lecture number 19. Yeah, complete sets. And the Ukrainian version of this course you can find on also in my web page, basic or algebraic theory of codes and automata. And we shall start. So, any subset of a code is itself a code. Consequently, it is important to know that the structure of maximal codes. Many of the results contained in this course of lectures are about maximal codes. The notion of complete set introduced in this lecture is in some sense dual to that of a code. For instance, any set containing a complete set is itself complete, even if the duality is not perfectly balanced. It allows us to formulate maximality in the term of completeness, thus replacing an extremal property by a combinatorial one. Let M be a monoid and let P capital be a subset of M capital. An element M of monoid M capital is called completable in P capital if there exist elements U and V of monoid M capital such that U multiply M multiply V belongs to P capital. It is equivalent to say that P capital meets the two-sided ideal M capital multiply M capital. So, or in other words, that M belongs to F capital of P capital, which is equal inverse of M capital multiply P capital multiply by inverse of M capital. A word which is not completable in P capital is incompletable. The set of words completable in P capital, of course, is of course phi capital of P, which consists of such element M capital inverse multiply P capital multiply inverse of M capital. The set F capital of P with bar is equal to M without F capital of P of incompletable word is two-sided ideal of the monoid M capital, which is disjoint from P capital. A subset P capital of monoid M capital is called dense in M capital if all elements of monoid M capital are completable in the set P capital. Thus, if F capital of P capital is equal M, or in the equivalent way, if the set P capital meets all two-sided ideals in the monoid M capital. Clearly, yet a superset of a dense set is dense. The use of the adjective dense is justified by the fact that dense subset of the monoid M capital are exactly the dense sets relative to some topology on the monoid M capital. An example: Let alphabet A capital consists of one element A small. The densest subset of the free monoid A capital star are the infinite subsets. Example next. In a group G capital, any non-empty subset is dense because G capital multiply M multiply G capital is equal to G for any element M from the group G capital. Example, the D code D capital of alphabet A capital consists to element A B is dense in free monoid A capital star in D. So what is the code here? We can see the monoid composed of the word on alphabet A capital having as many A's and B's. Let delta is morphism from A capital star to the group of positive integers by the morphism defined of delta of A is equal 1, delta of B is equal minus clearly the delta of the word is equal for all words from free monoid A star capital. Thus, such sets is equal to inverse image of 0. The base of delta inverse of 0 is denoted by d or d1. This is a monoid of itself is denoted by d capital star or d1 capital star. Word on D capital is called Dic primus. D is a Dic code our alphabet A capital. As I said, D capital star is the Dic set our alphabet A capital. And so, indeed, if W is a word of the free monoid A capital star, then the word of the such form A is the power to multiply the occurrence of the letter B and the word B, multiply W. B is the power of the length. The W is easily seen to be in the monoid D capital star. Furthermore, the non-proper non-empty prefix of V is in D capital star. Therefore, the word V is in D, showing that W is completable in D capital. It is useful to have special terms of codes X capital such that the submonoid X capital star is dense. A subset P capital of monoid M capital is called complete in M capital if the submonoid generated by the set P capital is dense. Every dense set is also complete. Next, a subset S capital of a free monoid A capital star is complete if and only if f of the image by f capital of x capital star is equal the free monoid A capital star. Example, any non-empty subset of the free semigroup generated by element I small is complete because it generates an infinite submonoid. Theorem. Any maximal code is complete. The theorem is a direct consequence of the following proposition. Proposition 2.5.6. Let X capital is a subset of free semigroup our alphabet A capital be a maximal code for any word from free monoid A capital star. One has X capital star multiply W multiply A capital star intersection with X capital star is not empty. The proof. The result is clear if the cardinality of the alphabet A is equal 1, or if the word W is an empty word. Otherwise, by proposition 1.3.6, there exists a word W prime from the free semigroup our alphabet A, so that y is equal W multiply W prime is unboarded. So we recall this the word W from free semigroup our alphabet A capital is called unboarded if no empty prefix of W is a suffix of W. In other words, the word W is unboarded if and only if W belongs to the following intersection: U multiply A capital star in the power plus intersection A capital star in the power plus multiply U implies that U is equal the empty word, where A capital the power plus is a free semigroup generated by alphabet A capital. And the proposition 1.3.6 states the following: let A capital star A capital be an alphabet with a least letter for each word U from the free semigroup A capital in the power A plus there exists the word V from the free monoid A capital star, so that U V is unbounded. So next week, since y capital is not a code, we have that x1 multiply so on multiply xn is equal yn and y1 so on multiply ym with m and n greater or equal 1, and xi xj belongs to the set y capital, and x1 is not equal to y1. Since the set x capital is a code, at least one of the x I y j is equal to y. Consider the leftmost occurrence of the word y among the x I y j. We may assume that it occurs among the x I, say at index k. Therefore, x1 so on x k minus 1 belongs to x capital, and x k is equal y. Let L be the least index such that x1 so on xn is a prefix of the word y1 so on yl. Set z is equal x1 so on xk multiply u is equal y1 so on yl. Clearly that z belongs to the following product: the product of the monoid generated by the set x capital star multiply y multiply the primonoid A capital star. So, and we can find this in this figure. We prove that x belongs to x capital star by showing that x1 so on xl belongs to x. Let p be the least index such that x1 so on xk minus 1 is a prefix of the word y1 multiply so on yp. Set x1 multiply xk plus minus 1 v is equal to y1 multiply so on multiply yp, with v is not empty because as I said x capital is a code. Therefore we get that xk multiply u is equal v multiply yp plus 1 multiply so on multiply yl. One has y1 so on yp belongs to x by minimality of the index k. Next, yp plus 1, so on, yl minus 1 are proper factors of xk is equal y, and therefore is also in x. Finally, xl is not equal y because the word y is unbordered. So yl belongs to x capital, the set of x capital, and the word z belongs to monoid x capital star. This completes this proposition. So example. We are able now to verify one of the claims made in previous lecture, namely that there do exist finite codes which are not contained in maximal finite code. Let X consist of the following word: a in power 5, ba square, a b b. It is a code. Our alphabet A capital is consist of letters A and B. Any maximal code containing S capital is infinite. Indeed, let Y capital is a maximal code. Our alphabet A capital containing code X capital, and assume that Y capital is finite. Set M is maximum of the length of the word Y, such as the word belongs to Y capital, and let U is the following word. U is equal B in power M, multiply A in power 4 plus 5m, and multiply b in the power m. Since as the code x y capital is maximal, it is complete. Therefore, we get that the word u is a factor of the word in the monoid y capital star. Neither b in power m nor a in power 4 plus 5m can be proper factors of the word in y capital. Therefore, there exist y and y prime from y capital as a unit with empty word, and integer p q r greater to equal 0, such that u is equal to b in power p, y a in power q, y prime b in power r, with a in power q belongs to y capital star. So you can find here this figure. The word a in power 5 is the only word in y capital which does not contain b. Thus, q is a multiply of 5. This implies that the occurrence of the letter y in the word a in the word y plus occurrence this word the letter a in the word y prime is equivalent 4 up to modulo 5. Let y is equal b in power h, a in power 5s plus I, and y prime is equal a in power j plus 5t multiply b in power k with n in j from 0 to 4. We have I plus j is equivalent 4 up to modulo 5, whence we get that 1 plus I plus j is equal to 4. We shall show that any choice of I and j leads to the conclusion that the set y capital is not a code. This yields the contradictions. If I is equal 1, j is equal 4, then k is equal or greater than 1, and we have that b multiply a capital a square multiply a in power 5t plus 4 and multiply b in power k is equal b multiply a in power 5 multiply t plus 1 multiply ab multiply by ab in power k minus 1. If a is equal 1, j is equal 3, then we have that the following factorization. Yeah. If I is equal 2 and j equal 2, we get the following factorization. Yeah. And in the case I is equal 3 and j is equal 1, then h is greater than equal 1, and we have the following factorization. And finally, if I is equal 4, j is equal 0, then we have the following factorization. This get a contradiction. This example is a particular case of a general construction. The conversion of theorem 2.5.5 is false. We show this in the example 2.5.8. However, it is true under the additional assumption that relies in the following definition. A subset P capital of a monoid M capital which is not dense is called thin. If P capital is thin, there exists at least one element M in monoid M capital which is incompactable in P. That is such that M capital multiply M capital intersection with P is an empty set, or equivalent F capital of P capital is not equal M capital. The use of the adjective thin is justified by result like proposition 2.5.8 or 2.5.12. Proposition 2.5.8. Let M capital be a monoid. P capital Q capital R capital is the subset of monoid M capital when the set the union P capital and Q capital is thin if and only if P capital and Q capital are thin. If R is dense and P is thin, then R capital without P is dense. Proof. If P capital and Q capital are thin, then there exist elements M and from M capital so that the following two conditions holds. Then element Mn is incompatible in the union P capital with Q capital, and therefore P capital as the union Q capital is thin. Conversely, if the set P capital is the union with Q capital is thin, there exists element M from monoid M capital which is compactable in the set the union of P capital and Q capital, and therefore incompatible in P capital and also in Q capital. Hence, P capital and Q capital are thin. If the set R capital is dense in the monoid M capital and P is thin, then R capital without P capital cannot be thin because otherwise R capital is equal R without P. The union with P will be also thin by the above statements. Thin subset of free monoid have additional properties. In particular, any finite subset of A capital star, of the free monoid A capital star is clearly thin. Furthermore, if X capital and Y capital are thin subsets of the free monoid A capital star, then the set A capital star multiply Y capital is thin. In fact, if U does not belong F capital of X and the V is element V does not belong to F capital star of Y, then we have that U multiply V does not belong F capital of the product X capital and Y capital. Example. The code D, our alphabet A, which consists of elements A and B are is dense, so we find this is proved in the example 2.5.3. It is a maximal code because it is a group code. For each element dx from D capital, the code D capital without element x remains dense in view of proposition 2.5.8, and the other remains complete. But of course, D capital without element x is no more a maximal code. This example shows that the converse of theorem 2.5.5 does not hold in general. Theorem 2.5.5 admits a converse in the case of codes which are both thin and complete. Before going on to prove this, we give some useful properties of these sets. Proposition 2.5.10. Let X capital be a subset of free monoid A capital star be a thin and complete set. Let W be a word incompletable in the set X capital. Then A capital star is the union, such union, where D capital and G capital are the set of suffix and prefix of the word W respectively. We shall prove this proposition. Let that is a word from the free monoid A capital star. Since the set X, since the monoid X capital star is dense, the word W is completable in monoid X capital star. Thus, for some U and V from free monoid A capital star, we have that UW that WV belongs to X capital star. Now, W is not a factor of the word in the set X capital. Thus, there exists two factorization. W is equal G1D is equal G D1, so that G1 DZ D1 and V is equal monoid X capital star. This shows that Z belongs the following set inverse of D X capital star G inverse. This completes this the proposition 2.5.10. Next proposition 2.5.11. Let X capital be a thin and complete subset of free monoid A capital star. For any positive Bernoulli distribution pi on the free monoid A capital star, we have that pi of S capital is greater or equal 1. The proof. We have that pi of the free monoid A capital star is equal to infinity. Since the union in equation 2, is finite, there exists a pair, an ordered part dg from d capital multiply g capital, so that p of d minus 1 x capital star g minus 1 is equal to infinity. Now d multiply such set d inverse of d x capital star inverse of g multiply g belongs to x capital star. This implies that pi of d inverse x capital star inverse of g multiply p of d is less or equal pi of x capital star. The positivity of the mapping pi shows that the pi of dg is not equal 0. Thus, we get that pi of x capital star is equal infinity. Now, pi of x capital star is less or equal such assume pi of x in power x capital in power n, where x belongs to the set of non-negative integer, is less or equal assume pi of x in power 1, where power n, where n belongs to the set of non-negative integer. Assuming pi of x capital is less 1, we get that pi of x capital star is less of infinity. Therefore, pi of x capital is greater or equal 1. This completes the proof. We know the following property showing us already claimed before that a thing set has only few words. Proposition 2.5.12. Let x capital is a subset of free monoid a capital star be a thing set. For any positive Bernoulli distribution on free monoid a capital star, we have pi of x capital is less than infinity, is bounded, yeah? The proof, let W be a word which is not a factor of a word in the set x capital, that W does not belong f capital star of x. Set n is equal to the length of the word W. We have that n is equal or greater 1. For I from 0 to 1 minus 1, consider x, y is consists of the such x from s capital, such the length of the word x is equal I up to modulo of n. It suffices to show that pi of x, y capital is finite from I is equal to 0, so on, n minus 1. Now, x capital I is subset a capital in the power I, multiply the free monoid over the set a capital in power n without the word w. Since the set a capital in the power n without the word w is a code, we have that pi of the free monoid over the set a capital in the power n without the word w is equal to the following axiom, yeah? Is equal to the following axiom. The positivity of pi implies that pi of w is greater than 0, and consequently we get that pi of the set which is monoid generated by the set a capital in the power n without the word w is equal to 1 divided by pi of w. Therefore, we get that pi of x capital I is less or equal 1 and divided to pi of w. This completes the proof of our proposition. We are now ready to prove theorem 2.5.13. And a thin and complete code is maximal. Proof. Let x capital be a thin complete code and let pi be a positive Bernoulli distribution. By proposition 2.5.11, we have that pi of x is equal or greater to 1, and by theorem 2.4.5, we have that pi of x capital is less or equal to 1. Thus, we get that pi of x capital is equal to 1. But then proposition 2.4.9 shows that the code x capital is maximal. Theorem 2.5.5 and theorem 2.5.13 can be grouped together to give theorem 2.5.14. Let x capital be a code our an alphabet a capital, then x capital is complete if and only if x capital is dense or maximal. Proof. Assume that code X capital is complete. If X capital is not dense, then it is thin, and consequently X capital is maximal by the prior theorem. Conversely, a density set is complete and a maximal code is complete by theorem 2.5.5. This complete the proof theorem 2.5.14. Before giving other consequences of these statements, let us present a first application of the combinatory characterization of maximality population. Let X capital be a subset of A capital free monoid A capital star be a finite maximal code. For any non-empty subset B capital of the alphabet A capital, the code X intersection with B capital star is a maximal code over alphabet B capital. In particular, for each letter A small from alphabet A capital, there exists an integer n that A small in power n belongs to X capital. The proof. The second climb results from the first one taken. B capital consists of one letter A small. Let n is a maximum of the length of the word which belongs to the code X capital. B a maximal length of the word in X capital, and let B is not empty subset with a subset of A capital. To show that Y capital is X capital intersection B capital star is a maximal code over alphabet B capital is sufficient to show in view of the theorem 2.5.13 that that's the set Y capital is complete in free monoid B capital star. Let W is the word with a free monoid B capital star, and B is a letter from the alphabet B capital. Consider the word W prime, which is equal B in power n plus 1, W B in power n plus 1. The completeness of the code X capital gives word U and V from the free monoid A capital star such that U multiply W prime V is equal X1, X2, so on, Xk for some X1, X2, so on, Xk from the set X capitals. But the definition of the integer n we get this, there exist two integer I and j so that n is less or equal I is less j is less or equal k, so that x I xi plus 1 so on xj is equal b in power r multiply w b in power s for some integer r and s from 1 to n. So it's demonstrated in the following figure. But then we get x, y plus 1, so on xj belongs to x intersection with b capital star, which is equal y capital. This shows that the word W is a complex table in Y capital star. This completes the proof of proposition. Let X capital be a subset of free semigroup our alphabet A capital be a finite maximal code, and let A small belongs to A capital be a letter. The unique integer n so that A in power n belongs to S capital is called the order of A relative to X capital. Theorem. Let X be a thin code. The following conditions are equivalent. X is a maximal code. There exists a positive Bernoulli distribution pi with pi of X capital is equal 1. For any positive Bernoulli distribution pi, we have that pi of X capital is equal 1. And the next, the fourth, X capital is complete code, yeah. Proof. The implication from 1 to first statement to 4 is a theorem 2.5.5 that any maximal code is complete. The implication from statement 4 to third is a consistent of theorem 2.4.5 and proposition 2.5.11. Yeah, the theorem 2.4.5 states the following: if X is a code, our alphabet A capital, then pi of S capital is less or equal 1 for Bernoulli distribution pi on Freemanoid A capital star. And proposition 2.5.11 states that let S be a thin and complete subset of the Freemanoid A capital star for any positive Bernoulli distribution pi on Freemanoid A capital star, because that pi of X capital is equal or greater to 1. And implication that statement 2, sentence 3 implies statement 2, yeah, is not very hard, and implication 2 implies 1 is proposition 2.4.9, yeah, which states that following: let X be a code owl and alphabet A capital. If there exists a positive Bernoulli distribution pi of Freemanoid A capital star, so that pi of X capital is equal 1, then the code X is maximal. This completes the proof of our theorem, which shows that these 4 statements are equivalent. Next, theorem 2.5.16 gives a surprisingly simple method to test whether a thin code X capital is maximal. It's sufficient to take any positive Bernoulli distribution pi and to check whether pi of X capital is equal 1. Example: the D code D our alphabet A capital, which consists of 2 elements A, B, is a maximal and complete, but satisfy pi of D is equal 1 only for one Bernoulli distribution. Thus the condition 1 plus 2 plus 4 do not imply condition 3 for dense codes. So example: the prefix code X capital with the union of such products A in power n, B multiply A capital in power n, where n is any positive integer. Our alphabet A capital is consists of 2 elements A and B, is dense because A is the power length of the word W multiply B multiply W belongs X capital for all W from Freemanoid A capital star. It satisfies condition 3, as have seen in example 2.4.11. We showed that in previous lecture. Thus satisfies the 4 condition of the theorem without being thin. And let X be a thin, next theorem, let X capital be a thin subset of 3 semigroup A capital plus, and let pi be a positive Bernoulli distribution. Any 2 among the 3 following conditions imply the said. The first, X is a code. The second, pi of X capital is equal 1, and the third, X capital is complete. So we show that the first 2 conditions imply the third. The condition pi of X is equal 1 implies that X capital is a maximal code by proposition 2.4.9. Yeah. Thus, by theorem 2.5.5 is the X capital is complete, that any maximal code is complete. And from proposition 1 and 3 implies the proposition 2. Theorem 2.4.5 and condition 1 implies that pi of X capital is less or equal to 1, yeah? Now, we get that X capital is thin and complete. In view of proposition 2.5.11, we have that pi of X capital is greater or equal to 1. Good. And the statement 2 and statement 3 implies statement 1. Let n is greater or equal to 1 be an integer. First, we verify that X capital in power 1 is thin and complete. To see completeness, let U belongs to the free monoid. The word U is a word from free monoid A capital star, and let VW the word from free monoid A capital star be such that V multiply W belongs to monoid X capital star. Then we get that VUW belongs to X capital in the power K for some integer K greater or equal to 0, yeah? Thus we get that VUW in the power n belongs to X in power n in the power K. This belongs to the monoid generated by the set X capital star in power n. This shows that the word U is completable in the monoid generated by the set X capital in the power n. However, since X capital is thin code, and because the product of two thin set is again thin, we get that the set X capital in the power n is thin. Therefore, we get that X in the power n is thin and complete. Consequently, pi of X capital in power n is greater or equal to 1 by proposition 2.5.11. Yeah. On the other hand, we have that pi of X capital in the power n is equal or less pi of X in the power n, and thus we get that pi of X capital in the power n is less or equal to 1. Consequently, we get that pi of X capital in the power n is equal to 1. Therefore, we get that pi of X capital in the power n is equal pi of X capital in the power n for all positive integer n, yeah? And proposition 2.4.3 shows that the set X capital is a code. Next. Thin codes constitute a very important class of codes. They are characterized by firm finiteness condition. We anticipate this result to prove in a particular case which shows that the class of thin codes is quite a large one. Proposition: any recognized code is thin. The proof: let X capital is a subset of free monoid A capital star be recognized as code, and let A capital Q I T capital be a deterministic complete automata recognizes the set X capital. Associate to a word W the number row of W is the cardinality of such product such states, yeah. The cardinality of such states where Q belongs to Q capital. We have that row of W is less or equal to the cardinality of Q capital, and rho of U W V is less or equal rho of W for all words U and V. Let J be a set of the word W in the free monoid A capital star with minimal value of rho of W. The previous inequality shows that J capital is a two-sided ideal of the free monoid A capital star. Let W belongs to ideal J capital, let P capital is equal such states Q capital multiply W, when P capital multiply W is equal to P. Indeed, P multiply W belongs to is a subset Q capital multiply W is equal P capital, and one on the other hand, P multiply W is equal Q multiply W square. Therefore, we get the cardinality of P capital multiply W is equal rho of W square. Since rho of W is minimal, we get that rho of W square is equal to rho of W, hence the equality. This shows that the mapping which posit P multiply W from P onto P is bijection. It follows that there exists some integer n as the mapping which P possesses P multiply P in power n, W in power n is in the identity mapping on the P capital. Since P capital is Q capital multiply W, we have the Q multiply W is equal Q multiply W in power n plus 1 for all Q with the set of sets Q capital. To show that the code X capital is thin, it's sufficient to show that X capital does not meet the two-sided ideal J capital. Assume that J capital intersects J capital intersects X capital, and let X small belongs to this intersection. Then we get that I multiply X is equal to T, which is belongs to T capital. Next, X belongs to G capital, and by the previous discussion, there exists some integer n, positive integer n, so that I multiply X in the power n plus 1 is equal to T. This implies that X in the power n plus 1 belongs to X capital. But this is impossible because X capital is a code. This completes the proof of the proposition 2.5.20. The converse of proposition 2.5.20 is false, as shown by the following example. Example 2.5.21. The code X, which consists of letters where n is belongs to the set of positive integer, so the set of the letter of the form a in power n, b in power n, if thin. For example, b a is not a factor of the set X capital, but X capital is not recognizable. Example. In one interesting case, the converse of proposition 2.5.20 holds a thin group code is recognizable. Indeed, let X capital is a subset of free monoid A capital star be a group code. Let phi is surjective morphism from A capital free monoid A capital star to a group G, and let H capital be a subgroup of G capital, so that X capital star is equal the inverse image of phi of the subgroup H capital. By assumption, X capital is thin. let M be a word such as incompletable in X capital. We show that H capital has a finite index in the group G capital, and more precisely that G is the union of such set H inverse image of phi of P, yeah, where P is less or equal M, where P runs over the prefix of the word M. Indeed, let G belongs to G capital and W belongs to the inverse image of phi of G. Let U is the word our alphabet A capital star, B such that phi of U is the group inverse of G phi of M. Then phi of the word W M U is equal G phi M phi of U is equal 1. Hence, V M U belongs to the monoid generated by set S capital. Now, element M is incompletable in X capital. Thus, elements M is not a factor of a word in the X capital, and consequently there exists a factorization M is equal P multiplied by Q, so that WP QU belongs to the monoid X capital star. Well, then we get that H is equal phi of the word W multiply P belongs to the subgroup H capital. Since H is equal to J phi of P, we have that J belongs to H capital multiply phi of P inverse. Yeah, this proves the formula. This is our formula. The formula shows that there are finitely many right codes of subgroup H capital in group G capital. Thus, the representation of the group G capital by permutation of the right coset of H capital is also finite. Denote it by K capital. Let alpha be canonical morphism from the group G to the right cosets K capital, be canonical morphism defined by the formula H multiply R alpha of G is equal H R G, when setting N is equal consists of the such sigma from K so that H capital sigma is equal H, yes, the image H is equal H. We have that H capital is equal inverse image by the alpha of the set N is equal inverse image of alpha of H. Well, we get that monoid X capital star is equal full free image on the psi of the image on the psi of X capital star. Hence, psi is equal alpha multiplied phi. Since the set K capital is finite, this shows that X capital star is the monoid is recognizable. Consequently, we get that the code X capital is also recognizable. Remark: we have used it in the preceding lecture argument, which really basically on two techniques: probabilities on the one hand, which allows to prove especially theorem 2.5.13, and direct combinatory arguments on the word on the other as in the proof of theorem 2.5.5. It is interesting to note that some of the proof can be completed by using thus one of the two techniques. A careful analysis shows that all preceding statements, with the exception of those involving maximality, can be established by using only argument on probability. As an example, the implication statement 2 implies statement 4 in theorem 2.5.16 can be proved as follows without using the maximality of the code X capital. If X capital is not the code X capital is not complete, then monoid X capital star is clean. Thus, by proposition 2.5.12, pi of X capital star is bounded, which implies that pi of X capital is less 1 by proposition 2.4.3. Conversely, there exists for some of the results given here combinatorial proofs which do not rely on the probabilities. This is the case for Theorem 2.5.13, where the proof given relies heavily on arguments about probabilities. Example 2.5.7 shows that a finite code is not always contain a finite maximal code. The inclusion problem for a finite code is the existence of the finite maximal code containing X. The inclusion conjecture claims that the inclusion problem is discernible. We prove the following remarkable property. Theorem. Rosenberg. Every rational code is contained in maximal rational code. Let M be a monoid. The family of rational subset of the monoid M is a smaller family R capital subset of M, such that the following three conditions hold any. First, any finite subset of M is in R capital. If X capital Y capital belongs to R capital, then the union belongs and product belongs to R capital. If X belongs to R capital, then free monoid R set X belongs to R capital. So then this family is called rational, yeah. So and when you consider the rational code, that the code which consists of the elements of free monoid, such that elements are these elements form a rational family, yeah. The proof of theorem 2.5.24 relies upon the result. Proposition 2.5.25. Let X capital is a subset of a free semigroup our alphabet A capital be a code. Let Y belongs to free monoid A capital star be an ordered one such that A capital star Y multiply A capital star intersect X capital star is not empty. Let U capital consist of such word from such sets A capital star without such set. When the set Y which is equal X capital union Y multiply U capital Y in star is a complete code. Proof. We denote V capital is A capital star without A capital star Y A capital star. Then by assumption X capital star is subset V and U is equal V without X capital star. Let us first observe that the set Z capital V capital Y is a prefix code. Assume indeed that V Y is less V prime Y for two words V prime from W. Here must be comma, yeah. Since the word y is unbounded, vy must be a prefix of the word v prime. But then v prime is lies in the set a capital star y a capital star a contradiction. Therefore, we get that z capital is a prefix. Now we show that the set y capital is a code. Assume the contrary and consider the relation y1, y2 multiply so on, yn is equal y1 prime, y12 multiply so on, m prime with yi and yj prime belongs to set z capital and y1 is not equal to y1 prime. The set x capital being a code, one of these words must be lies in the set y capital without x capital. Assume that one of y1, y2, so on, yn is in the set y capital without x capital, and let p be a smallest index so that yp belongs to the set y multiply u capital multiply y in the power star from y this relation. It is also problem that yp does not related f capital of x capital star. Consequently, one of y1 prime, y2 prime, so on, ym prime is in this set y multiply u y star. Let q be a smallest index such that yq prime belongs to the set y multiply u capital Y star. Then we have that y1, y2 multiply so on, y multiply yp minus 1 y prime 1 y prime 2 multiply so on, multiply y prime q minus 1 y belongs to the set z capital. Hence get that y1, y2, so on, yp minus 1 is equal y1 prime, y2 prime, so on, y prime q minus 1, because the set is that capital is prefix. The set x capital is a code, thus from y1 is not equal 1, y prime 1 is follows that p is equal q is equal 1. We set y1 is equal y multiply q1 y so on y uk multiply y and y prime 1 is equal y u prime 1 y so on y u prime l y with y I and y sorry with u1 is so on uk u prime 1 so on u prime l belongs to u capital. Assume that y1 is less y prime 1. Since the set z capital is prefix, the set z capital star is right, so the monoid is z capital star is right unitary from the inclusion of u capital belong is a subset v capital is follows that each u I y u prime I y is in z capital. Consequently, we get that u1 is equal u1 prime, so on uk is equal u prime k. Let t be the word the following u prime k plus 1 y, so on u prime l y. We have that the word y is a factor of t and thus occurs also in the word y2 so on yn. This shows that one of the words y2 so on yn, say yr, is in the set y multiply u capital Y star. Suppose r is chosen meaning null, then y2 so on yr minus 1 y belongs to that capital, and use prime k plus 1 y belongs to z capital are prefixes of same words. With the set z capital being prefix, we have that u prime k plus 1 is equal y2 so on yr minus 1. Thus we get that u prime k plus 1 plus 1 belongs to monoid x capital star, in a contradiction with the hypothesis that u prime k plus 1 belongs to u capital. This shows that the set y capital is a code. Finally, let us show that code y capital is complete. Let w is a word from the primonoid a capital star, and set w is equal to y1 v1 y v2 y so on v1 minus 1 y vn, with n is a positive integer and vi belongs to the set I capital star without I capital star y a capital star. Then we have that y belongs to the monoid y capital star. Indeed, let vi1 va2 so on vik be those vi's which are in monoid x capital star. Then we get that wy is equal to this. Yeah? Each of these parentheses word is in the code y capital. Thus the whole word is in y capital star. This completes the proof. Next we prove theorem 2.5.24. Since the set x capital is irrational, the set v capital defined in equation 3 u is that capital is that is also rational. Thus y capital is a rational code. By proposition 2.5.20, the set of y capital is thin. So this, by theorem 2.5.13, it is follows that the set y capital is a maximal code. And this completes the proof of proposition 2.5.24. Example: let alphabet A capital consists of two letters A and B, and X consists of the word A, B. The word Y, which is equal to BBA, is unbounded and is incompletable in the monoid X capital star. The deterministic автомата recognized as the set U capital is given in the following figure. According, we obtain after some reviewing the expression that U is equal U capital is sought. Consider Bernoulli distribution pi on the primonoid A capital star and set P is equal pi of A, Q is equal pi of B. Then an easy computation shows that pi of U is equal 1 divided to PQ, and thus P of Y capital is equal 1 for the set Y capital defined by the formula 3, yeah? Which implies that the code Y capital is maximal. Next example, we consider the following alphabet and the following code. The word Y, which is equal ABA, is in the complex table in the monoid X capital star. However, X is the union with element Y is not a code because we have such factorization. This example shows the proposition that proposition 2.5.25 is false without assumption that a word Y is unordered. The following propositions show how the property of being a complete code is reflected in automaton. Let X be a subset of P subgroup A capital plus, and let A Q11 be a tree automaton recognized monoid X capital star. Then X capital is complete if and only if the transition monoid of the automaton A capital does not contain a null relation. We prove. If X capital is complete, then for each word from W from Freemonoid A capital star, there exist two words U and V from Freemonoid A capital star, so that U W V is equal belongs to X capital. Then there exists a path from 1 to 1 here. This implies that order power PQ is in phi of W, and consequently phi of sub A of W is not a null. Consequently, if pi of A capital star does not contain the null relations, here must be pi, yeah. Then for each word from Freemonoid A capital star, there exists at least one path from PQ with label W. Since automaton A capital is stream, there exist two paths from empty word to P with label U and from Q to 1 with label V. Then we get that U W V belongs to X capital star. And therefore, X is capital is complete. For a commutative polynomial, P from Q of A capital, whereas Q is capital are polynomial our alphabet A capital, and a Bernoulli distribution pi on the alphabet A capital, we denote by pi of P the number obtained by substituting pi of A to the letter A for all A from alphabet A capital. More precisely, setting A capital consists of A1, so on A_n, and P is equal P of A1, so on, and A_n. And the number pi of P is equal P of PA1, so on, pi of AN. And the following result will be used several times in the sequel. Proposition 2.5.29. Let P be a polynomial, the set of polynomial, our alphabet A capital, and let A is a letter from the alphabet A capital. The following conditions are equivalent. P is divisible by the polynomial 1 minus assume A, where A belongs to A capital. Pi of P is equal 0 for each positive Bernoulli distribution. The proof that implication that the first statement implies the second statement is clear. We prove that first statement follows from second statement. To prove this implication, fix the letter A small from capital A capital and set B capital is equal A capital without letter A small. Consider P as a polynomial in the variable A small with the coefficient in the set Q capital of B capital. Similarly, consider polynomial the sum of A from alphabet A capital A minus 1, which is equal A plus U as a linear polynomial in the variable A small with constant term U, where U is equal to the sum B, where B from B capital minus 1. The Euclidean division of P by A plus U gives P is equal Q of A plus U plus R, where Q is polynomial our alphabet A capital and R is a polynomial our alphabet B capital. Since pi of P is equal to 0 and pi of A plus U is equal to 0, for each positive Bernoulli distribution pi, the polynomial R vanishes at all points Z with coordinates Z1, so on, n minus 1, which belongs to the Q capital in the power n minus 1, so that Zi is greater 0 and then 1 plus so on plus that n plus minus 1 is less or equal 1. It follows that R vanishes and consequently we get that 1 minus sum of A, where A belongs to A capital, divides P. This completes our proposition. Recall that alpha denotes the canonical morphism from Q of A into Q of A third. So let X be a finite maximal code on the alphabet A capital. Then alpha of X capital underline minus 1 is divisible by alpha of A capital underline minus 1. Proof. Let P, what is X underline? For any subset X capital of the Freemonoid A capital star, we denote by X capital underline the characteristic series on the set X defined by the following formula. So let pi be a positive Bernoulli distribution of the Freemonoid A capital star. By theorem 2.5.16, we have that pi of X is equal 1. By proposition 2.5.29, this implies the conclusion. And example, for the code X capital, it consists the word AA, BA, BB, BA, A, B, B, A. On the alphabet A capital, it consists of two letters A and B. One has alpha of X capital underline minus 1 is equal B plus 1 multiplied by A plus B minus 1 multiply A plus 1. So I finish my long lecture, and I wish you good health, good luck, and goodbye.